Okay. All right, well, we'll just go ahead and get started then. Nothing new on the assignments or business aspects of things. I'll be telling you about some new stuff that's going to be coming up. I just want to I'm going to be doing this for a while. I'm repeating myself every day for a few days. The whole business about these conference recordings, how they disappear after 14 days. And if you want a recording of them, you better get it before 14 days. Better download a copy before 14 days, or they're going to disappear. There's another aspect that's actually, if I have time today, I'm going to get into. Where right now I'm doing all of this stuff through a webcam, and that seems to work through Big Blue Bubble or whatever it is that we're using. Yeah, that's why I'm relying on. If you want to do that, feel free. I mean, I've got a whole bunch of other stuff. Just trying to get this stuff ready for you guys online. I don't have an assistant that helped me with all this audio-visual stuff. And boy, when we come, on November 3rd, we're supposed to come back in a hybrid mode, and then my workload is going to double because of the dumb way that they organize that at the district level. And that's going to be a real mess. So, one of the things about the recordings is on Big Blue Bubble is there's two things that you can do. You can share a webcam or you can share a screen. And when I did this once before with my regular class, not with you guys, but with a regular class, showing them how to do one of these online simulation labs, which I'm going to have you guys do here in the next few days. It's kind of a cool little, as simulation lab goes, it's not bad the way that it works. But I have to it's not through Canvas, it's through a different website altogether that you have to access, and you have to access it in a very specific way or it's not going to work, you won't be let in. And then what you actually do, I have to walk you through it the first time. So you understand what it is you're doing and what you have to submit for an assignment. It's a little bit confusing because you're hopping back and forth between platforms. So I have to share a screen with you. And when I did this before, and Big Blue Button just didn't record the shared screen. At least it shared it and you could see it on the recording, but when it came to like downloading it, it wouldn't you like move your cursor over the screen that for my webcam and then right click and it says save video as. When you did that with the screen, there wasn't anything there. You couldn't save it. So you have to resort to some sort of app or add-on to your browser. And I think there's I think almost every browser has an add-on where you can record the screen. So you have to do you have to get an add-on to your Chromium browser if you're using Chromebooks or whatever, or Apple, or I don't know. I had to get one for Firefox, and it worked. I was able to record it, but anyways. So when this thing gets done today, and if I get to that point in the and I can show you that lab and those other website, then try and get grab a screenshot of that or get a recording of it. And if you're having trouble, let me know. Okay. Anyways, so that's we'll get to that in a second. I got to go through a few practice problems before I can get to the lab, because the lab involves the concepts that we're going to learn in these practice problems. All right, but not this particular problem. Well, kind of this particular problem in a way, but more so the next problems. Anyway, so this is the second problem on this worksheet that we got. I didn't have time to finish yesterday. Motion in one dimension with where you have an object that's accelerating. Here we have a problem where you got two objects that are moving along an x-axis, and we have to set up the equations of motion and see if we can answer the question. Okay, so sorry, I don't know why I used English units. should go back and change it. That could be easy to do. Anyways, they're just numbers, and they work out. You don't have to worry about the units specifically. So you got a car, 2 cars actually, and the first car is on a straight highway, a straight, one-dimensional highway. It's a straight line, but the line kind of goes up over the top of the hill, and so as soon as the car reaches the top of the hill, there's only one lane to the highway, and there's no shoulders. It's like it's a one-lane highway down through a cavern, through a canyon, which has sheer rock walls on each side, so you can't get off the road. So you have no choice but to stay on the one-lane highway. Maybe I should have used a train. I don't know. It made more sense. Anyways, so it reaches the top of the hill and sees another car on this one-lane highway, a tenth of a mile ahead of it, traveling 10 miles per hour. You're traveling 80 miles per hour, so you're going much faster than this car in front of you. You've totally neglected the maintenance on the car, and your brakes are terrible. They're all worn out. It's just metal scraping on metal at this point. So when you slam on the brakes, the most you can decelerate is at 2 miles per hour squared. So given that deceleration, the question becomes, if you're already overtaking the second car, can you slow down fast enough to keep from colliding with a car in front of you? That's the question. Okay, and how do we show it mathematically? All right, does everybody understand what the problem is asking? You got a car overtaking a slower car from behind. It can only decelerate, decrease its velocity at a certain rate. Okay, is that rate good enough to keep it from colliding with the car in front of it? So you can slow down from 80 miles an hour to 10 miles an hour in the space they're separated by when you first slam on the brakes. Does that everybody understand what the question's asking? This is like this is what why physics tends to be kind of a difficult subject, is because a lot of times you read the question, you're like, I have no idea what this question's asking. So that's the first step. Do you understand what the question's asking? Okay, and once you go there, then you can start to set the problem up. So I'm seeing nobody asking for, so I'm just going to go ahead. Okay, so first things first, let's set up a little coordinate system. Okay, in this case, coordinate system is kind of a nice thing to start with. So there's an x-axis, right? All right, and in fact, I didn't put this in, but let's call this 0. Okay, that's the origin for the x-axis, right? Okay, let's call the first car that's traveling at 80 miles an hour car A, and the second car that's traveling at 10 miles per hour car B, and set up the problem. Okay, so how are we going to solve this problem? Is there a collision? Okay, that's the question that's being asked. Is there a collision? So my question to you guys is, okay, what is this problem going to involve in terms of the solution? We have, first off, what equations would we use to solve this problem? Is there a set of equations of motion that we already know, hint, hint, that we could use, given the fact that one car is traveling at a constant velocity and the other car is traveling with a constant deceleration? Do we know equations that we already have that are at our disposal that we could just start with, rather than, Minkowski equations? Okay, all right. Don't write that down on the AP test if you take the AP test. Okay, I don't think they'll find. Remember, the AP test is graded by a bunch of grumpy old physics teachers. So the answer is yes. We can use the kinematic equations to set all of this stuff up. Okay, but which one? And you correctly pointed to the right one, the position equation. Okay, why the position equation? Because if there's a collision, they have to be at the same place at the same time, right? So their positions must be equal at the same time. and that's what's going to determine whether or not they collide. So it makes sense, I think. Does it make sense to everybody that we should start with setting up the position equations? The velocity equations, there's really nothing they're asking about like what would be the relative velocity at a certain time or something like that, where you'd need to subtract the velocity equations. So it's the positions we're interested in, okay? Plus the fact that I wrote down an x-axis. Okay, now for car A, the kinematic equation for position is 1/2 at squared plus v0t plus x0. So for car A, the way I've got the thing set up on the x-axis, what would be, say, the initial position for car A? Zero is correct. Very good. Okay. Yeah, because I placed the A at the origin. What would be the initial position for car B? Right, 0.1. Now see that this is a problem where you actually do have to have an initial position for one of the cars, right? That car B can't start at the origin because that's not what's given in the problem. The problem is set up so that the car B is already at 0.1 on the x-axis if car A is at 0 on the x-axis. Okay, what is the initial velocity for car A? Right, 80 miles per hour, right. What's the initial velocity for car B? 10 miles per hour, correct. All right, what's the acceleration? What number do I have to put in for the acceleration for car A? Be careful here. Yeah, -2. That was what I was looking for. I was looking for the negative number, right? It's the deceleration. So you have to put that number in as a negative. Every hour that goes by, you subtract 2 miles per hour from your time. Okay, I think you guys understand what the answer to the problem is going to be at this point, given the ridiculous numbers I used. Anyways, now here's another one though. What is the acceleration for car B? It's not explicitly stated, but you can infer it. Yeah. So the answer is 0. It's not. The car B is just traveling at a constant 10 miles per hour. It's not increasing or decreasing its velocity. So its acceleration is 0. So there we go. That's all the information we need. So if I plug all that information into the x equation for A, I'm labeling it the x sub A. That's position A of that car A. It's going to be -2 for the acceleration, 80 for the velocity, and 0 for the position. I'm leaving out the units for now, just to keep things simple. I shouldn't even have used English units. Okay, so for car B, what did we say? Acceleration was 0, the initial velocity is 10, and the initial position is 0.1. Okay? All right, is everybody happy with that one? Any questions about any of that? So there's the two positions as function of time for each car. And now where do we go? So okay, so now we got a math problem, but it's both a physics and a math problem. What is the condition? We already said this. What is a condition for a collision? They have to be at the same position, right? Now, okay, so we're going to do that, right? We're going to set x of A equal to x of B, and more like give us mathematically. It'll give us an equation involving just t. How are we going to know whether or not there's a collision just from that equation in time? What if, you got one position A moving along, one position B moving along? What would happen mathematically if x sub A never equaled, never equaled x sub B at any real time t, right? T, and you got an equation in t, you might get a solution, right? But it would be a funny solution. The number you would get out might be imaginary. But what does that tell you? It tells you that there's no real time t where you get an answer. So there's no actual time where there's a collision. So does that make sense to everybody? Here's another way of looking at it, and I'll probably put this on a post-it again. But think about, what you're doing here is the same thing you did in math class with linear equations. Remember, they used to do linear equations, and they used to say, okay, you got two equations in x and y. There's three possibilities. There's one solution if the two lines intersect at a point. There's infinite solutions if the two lines are on top of each other, and there's no solution if the lines are, parallel to each other and not on top of each other. So start thinking along those lines. All right, so the basic way of solving this is you set x of a equal to x of b, and then see if there's a solution for t. Really say see if there is a real solution, a real number t for t. Okay. All right. So if I do that, set the two equations equal to each other, and then you got to play games. Uh-oh, there's a t squared in there. Darn. Because you know what that means. That means you got a quadratic equation. Okay. So what do we do with quadratic equations? What would you do in a math class? The answer is you'd factor it, right? You'd factor the quadratic equation. Well, I'm here to tell you, unfortunately, that all those months you spent learning how to factor quadratic equations were a complete waste of time, because in the real world, quadratic equations never factor. So there is you can't factor that thing. So what do? You use the quadratic formula. That's the only thing you ever do with quadratic equations in the real world. Yeah, I know. I think back, like, all those quadratic equations that they made me factor, and it's a completely useless skill because quadratic equations never factor in the real world. Anyways, but you got the quadratic formula, right? It's what is it? It's how does it work again? Is it minus? It's minus b plus or minus the square root of b squared minus 4ac, all divided by 2a, if I remember correctly. Did I get that right? Okay, I think I got that right. Anyway, you go look it up in a book or the internets. And you get two solutions because it's a quadratic formula. Okay, one solution is, I should have rounded it off to 70 hours. Okay, the other solution is 0.0014 hours. Okay, so, we have to do a little bit of thinking about this. Like, why do I get two solutions and which one is the one I use? So, one car is overtaking the other car, and there's two times. This is what it's telling. I get two real solutions, right? So there's two times at which the positions are the same. So which time do you think I should take? The first time, or the smaller time, or the bigger time? And of course, the answer, on there is the smaller time, right? So I didn't even write it down. So is there a collision? And the answer is yes. There's a collision. So there's. Now here's the thing. Between. Here's the thing that's going on here. I'm going to make a little drawing here. All right, here's what's really going on here. Okay, you have what we're doing here is we're taking a quadratic equation, which is the x squared one, and we're setting it equal to a linear equation, 10t plus 0.1. Okay, and by doing that, we're basically saying, okay, where are the intersections between those two equations? And from a graphic point of view, they're both x of t equations. We're asking, what are the intersection points? It's just like what you did with, linear equations in x and y. Does this make sense to everybody? And so we're trying to ask, okay, you know, as x, here's this is x sub a here, and this is x sub b here, right? And so x sub a is decelerating, and so it's a parabola opening downwards, okay? X sub b is just traveling with a constant velocity, and so it's a straight line. And so if they weren't in the same lane, right? If they could pass each other, then you know this would be the equation of x sub a, and this would be the equation of x sub b, right? And so so at this point here, you know, they're at the same place at the same time, and there's a collision. Well, at that point, from a physics point of view, the problem ends, right? Because you don't have cars anymore. You just have flaming wreckage, okay? But from a mathematical point of view, the problem continues because the math doesn't know that, you know, the cars crash into each other and burn. Does that make sense? So the math keeps going because, you know, we're just using math here, okay? These are just equations. So the math says, okay, car A decelerates and keeps decelerating to a stop, and then the -2 miles per hour, where'd it go? The -2 miles per hour continues. And the math doesn't know that the car, you know, the brakes would stop and then everything would stop. It's just it's a negative deceleration. It's like throwing a rock up in the air. Once you reach the top of its motion, it keeps coming back down. It starts coming back down again. So that the -2 keeps going. So it comes back down again. And so the car, according to the equations, the car would slow down, stop, and then start going backwards. That's what you put into the equations. So, you know, from the mathematics point of view, the car doesn't. It blows right through the second car, stops, and then comes back and crashes into it from the back, you know, going backwards from the front. But, you know, of course, that's just the math. Okay. So, does that explain? I wanted you to understand why there's two solutions. It's just a mathematical artifact to the way this works. Well, well, it depends upon, you know, you'd have to actually do the math and actually graph these correctly, because there's a possibility that this point could be over here and it would catch it, you know, on the way up as well. I just kind of drew it this way just to show you why you would get two solutions. You'd have to go through and do the math and actually graph it with the numbers to see what actually happens. Okay, does that make sense? So whether the car stops before the second car collides with it a second time has to do with the numbers involved. And like I said, you'd have to get a graphing program and you know, put the actual numbers in to see what happens. Okay, I just wanted to show you why you get two solutions and why, because this happens a lot in physics where you get two solutions, say, and you have to figure out which one is the correct solution to the physical problem that you're solving. Okay, and when they first collide, the problem ends. Okay, there is no second collision. You only can collide a car once, and then it becomes a different problem altogether. Does that kind of make sense? That's the point I'm trying to make. All right. All right, can we move on to the next? Any questions on this? All right. Let's do this way first. Okay, so I'm going to get rid of this guy. All right. All right. So here is here is a problem. Okay. You have a problem moving in a straight line, right? Okay, so we're still in one-dimensional motion. And now I'm going to do a velocity versus time sketch. Okay, well, graph in this case, because there actually are numbers. And you can see the velocity increasing and then decreasing and then increasing again as a function of time, right? Okay. And the question is, sketch a graph that represents the acceleration of the object as a function of time. Now, here's the thing, since they're using this wording, sketch. Do you guys understand the difference between a sketch and a plot? Okay, a plot is where you make a little table, and you put in a bunch of numbers, like say from 1 to 10, and then you plug them into the equation. You get a second set of numbers, and you put the dots on the graph, and then you connect the dots, right? That's a plot. Okay. In this course, especially when it comes to the AP exam, they will oftentimes ask you to make a sketch of what's going on. Now, a sketch does not mean a plot. There's no table, there's no dots, you don't connect the dots. You just kind of do a freehand sketch of what's going on. The idea is just to get the right curve shape and maybe hit a few important points on the axes. Does that kind of make sense? So it's not as mathematically correct necessarily as a plot. They're just looking, do you get the right shape? Do you get the right, like vertical intercept? Is the vertical intercept correct? Or is the horizontal intercept correct? Something like, things like that. Is the slope of your line positive or negative? That sort of thing. That's what they're looking for when you sketch something, okay? So when they ask for the acceleration of a velocity versus time graph, what are they actually asking for? And this goes back to calculus. And the idea of what is the graphical interpretation of a derivative. Yeah, the derivative of the time graph, but from a graphic point of view, what is that? Yeah, it's the slope of the tangent line, exactly, right. So think about, as you go up this curve, what is the slope of a tangent line? Well, it starts out like that. Okay, and then what happens as you go along the curve? What's happening to the slope? And you see that the slope starts to increase, right? And then when it reaches some point right about there, right, what happens to the slope? It stops increasing and starts decreasing. And there's actually a name for that point. Yeah, you got it. I'm not fooling anybody here. Good. You guys remember that term inflection point? That's what an inflection point is. It's where the slope stops increasing or starts decreasing, or vice versa, right? Okay. Titrations. Wow, you did that in chemistry? I'm just talking about math. That's impressive. Okay. Wow. Cool. All I remember is doing that lab and got the little valve on the titration pipette thing, and you're supposed to, as soon as it turns pink, you're supposed to shut it off. And then of course I rotated the wrong way and turned it full on and ruined the experiment. That's all I remember from chemistry class. It's always like, darn it, now I got to do it all over again. Rotated the wrong way. Anyways, so inflection point, right? Okay. So since the slope is the acceleration, what's going on from 0 to that inflection point? What should the graph of acceleration look like? It should be increasing, right? And then from that inflection point onwards, then it should start decreasing, okay? And then what should the acceleration at t equals 2 seconds be equal to? Right, exactly, 0, because the slope is 0. And then on from there, and we'll sketch this graph. Now, here's the problem with this guy. Are you given any sort of actual functions here? I'm not exactly sure. Maybe this might be, you might be able to construct the shape of a graph with maybe like a cubic or something like that. I don't know. But anyways, here's my point is from 0 to where that pencil point is pointing, what do you think the actual function of velocity versus time is? It's increasing, but the problem doesn't give you any indication of how it's increasing. Is it increasing with the square of the time? Yeah, is it a sine function? Is it an exponential function? Is it going up cubically? You don't know. So, and the answer to that determines what the shape of that if it was square, if it was let's say there's a thing where you can kind of patch functions together. It's called a spline function. And you can piece things together. So this thing could have been pieced together out of t-squared functions, right? In which case, if you took the derivative of a t-squared function, you'd get a straight line, right? And so, but you don't really know. So the actual answer to this guy is actually not completely understandable. I'm assuming that all of these curves, that's this guy, when he made this graph, he pieced together a bunch of t-squared functions, either with a positive or a negative, t-squared coefficient. Does that kind of make sense? Does that make sense what I'm saying? So that if you go from 0 to that inflection point, it's a t-square relationship. So the a versus the acceleration would be a straight line. Right? Yeah, kind of, sort of. Okay. Now, I don't know that for sure. So the answer is a little bit on the ambiguous side. Okay, but all I do know that is that at t = 1, at that inflection point, a stops going up and starts going back down again, right? And I'm assuming that this part from 1 second up to the maximum at 2 seconds, that's going to be another t-squared relationship. So I'm assuming all these relationships between velocity and time are t-squared relationships, which may or may not be true. Okay, so I hope that doesn't confuse you guys. All right. Now, the only thing you got to be a little careful is, and I don't know if I really made it obvious, is that transition point there cannot be a jump discontinuity in the slope. It has to be curved a little bit, right? Things are always smooth and continuous in this course, right? Did that make sense what I just said? Right? The slope of this guy can't go from positive to negative in one little instant. It has to be more kind of curved over. Let me try and draw it in. Curved over at the top a little bit more. Hopefully that made sense. Because everything in physics is smooth and continuous. Okay, so at t = 2 on this graph, what should the value of a be? You already told me, right? 0, right? So that's where it crosses through the horizontal axis at t = 2. And afterwards, from this inflection point to this inflection point, the slope is getting smaller, right? Even though, and it starts getting negative past 2, but it's still decreasing. And then there's another inflection point somewhere in here somewhere where the slope starts, becoming positive again. So I put that a little bit past 3. It was a little hard to see on the graph. All right. And then there's even a third inflection point right here. Okay. And I put that at x = 5. And so, no, I guess I got it a little bit wrong there. And so you kind of, the answer is a little bit on the ambiguous side, but this is the idea, is that, from a graphic point of view, the acceleration is the slope of the tangent line, and you can get things like inflection points and 0 points, and that's how it ends up being graphed. Okay, any questions on that? Yeah. Okay, all right, on to the next one then. All right, get rid of this guy. All right, so now we're going to do kind of the opposite now. Right. And put this up at the top so you can see it. Okay, so here's another velocity versus time graph. By the way, this I don't know. They don't use. I noticed they've stopped doing this so much on the AP tests over the last several years. It used to be a favorite problem of theirs to give you a graph that's a bunch of line segments. And then ask you something about it. I've seen them do that in a few years. You never know. This could still happen. So here's an object's velocity given by the following above graph, and you notice that it's made up of line segments, and they've delineated the different line segments out along the axis, and they've labeled them A, B, C, D, and E. Find the distance the object has traveled during each time interval and the total distance traveled. Okay, so I should have maybe used the term displacement instead of distance, but in one-dimensional motion, it's kind of the same thing. All right. So how do I get from velocity to displacement or position? Going from velocity to acceleration is the derivative. Going the other way, yes, is right in the integral, and the integral is the area under the curve. That's the whole idea behind the graphic point of view. Is that you've got to remember that the integral, which is the opposite of differentiation, it gives you the area under the curve. Okay, it's the area under the curve. All right, and so this was the trick that they used to throw on AP tests all the time. It's like, okay, so how are you going to get the area under this curve? Well, I suppose you could do, take the first line segment A, and that's going to be a line, that's going to be a velocity versus time equation, which has a slope of 10 over 10. So 10 meters per second squared times t plus an intercept of 0. And then integrate that from 0 to 10. Now, are we going to do that? Does it make sense to do that? To find the area under the curve? Or wouldn't it be easier just to say, oh, the area under the curve is a triangle and it's 1/2 base times height? So that's literally what we're going to do for this problem. We're going to go for each segment of time. We're literally just going to find the area under the curve by adding up the areas of triangles and rectangles. And that's the trick. Does that make sense to everybody? Okay, so I'm going to move this up here so I can try and keep the graph on. Okay, so area A. Does it make sense that it's just going to be 1/2 the base, which is 10, times the height, which is 10 meters per second, 10 seconds times 10 meters per second. You put the units in there because they're important, and then because it gives you the correct units out. So the base, which is going to be 10 seconds, and the height, which is going to be 10 meters per second, multiplies together to get 100 times 1/2 is 50. Meters per second times seconds is meters. So in the first segment, 10 seconds, you've traveled 50 meters. Does that make sense to everybody? Yeah? Okay. What about the second one, B? Well, does everybody see a small little triangle sitting on top of a rectangle? From 10 to 20 for segment B? Okay, so I can't keep both in the same. I got a little bit of room down there. Zoom out a little bit. Still see it. Okay. All right. So for B, I've got a rectangle that's going to be from 10 to 20. So that's 10 seconds times, and it's got a height of 10. So that's 10 times 10. And then the little tiny triangle on top is going to have a base of 10 and a height of 5. Does that make sense to everybody? And so do all the math there, you get 125 meters. Okay, C is just going to be one big rectangle, 15 times 20, so you get 300. D is going to be another small rectangle, or square, on top of a triangle. I'm running out of, I can't zoom out, or you won't be able to see it. Okay, we got that makes sense so far? Good, good, good. Okay, and then E is just a triangle. All right, I've run out of room here. So a triangle, 1/2 5 times 20. All right, come back up here. You can see there's 20 for the time and 5 for the height, right? So 5 times 20 times 1/2, that's another 50. And then what? You add them all up, right? Now, just one little thing about this. What if the curve had dropped below the horizontal axis, and the curve actually went into negative velocity territory? What would you do? What would these what would happen to these numbers here in those areas where you're below the curve? Yeah, the area would have to be considered negative, so you'd have to subtract them from the total. Does that make sense? So these are all positive velocities, right? So we're going in the positive x direction. If we were to go below the axis, they would be negative velocities, and we'd be traveling in the negative direction along the x-axis. So you'd be subtracting from the total distance, or the total displacement. All right, but these are all positive. So you add them all up, and I get 625, and that's the answer. All right. Any questions on that? All right, so now I'm going to attempt to do this. I'm not, it's like I'm just thrown in. I'm not an expert on this online teaching stuff. All right, so there's this. It's not even your book. It's actually the regular physics book, but fortunately, you guys are all signed up on this website for the regular physics book, and I already assigned this to my regular physics students, and it was a bit of a mess because the lab was actually kind of beyond the scope of mathematics that you could expect in the course. The lab actually involves a bit of calculus understanding, and so it's my regular students had a bit of problems with this lab, but you guys should be able to handle it because a large part of this lab has to do with this graphical interpretation of these quantities, and so you guys should be able to do this. In fact, what you're going to be doing in the lab is kind of what we just did on this graph. You're going to be finding the area under a curve for this motion stuff. Okay. So let me get rid of this guy, and I'm going to see how it is. I'm going to stop sharing my webcam for now. Okay, and then I'm going to hold on a second. I got to do this. See if I can get this working here. Okay, I'm going to share my screen. That's the one. All right. All right. Can everybody see my Google homepage? Yes? Okay, Google homepage. All right. Can you see my cursor, by the way? No, you can't. Unless I go over here. Now can you see my cursor? Here's the problem, though. I can't see you guys if I do this. Okay. Let me move this over here. Can you see my cursor wandering around in a circle? Okay, good. This is so complicated. I don't know why this it's so complicated for me. I should know how to do this stuff. Anyways, now, is my cursor over the G in Google, or is it off to the side? No. My cursor's not there? Okay, is it over? Maybe it disappears when I stop moving it? Teleportation. It blinks? Oh God, that's, I'm planning on doing demonstrations, but when you play a video on a shared screen in Big Blue Button, the frame rate goes down to like 1 frame every half a second. It's absolutely ridiculous, and so you can't even. I can't do videos through Big Blue Button. I can't do live demonstrations. I don't know. So maybe I'll have to do Zoom or something. Or what I've been doing is just recording them and posting them up there. Anyways, all right. So hopefully you can see my little cursor there. Hopefully it's in the right position. Because when I looked at it the last time, the cursor was displaced off to the left by a few inches. So, and that gets really confusing. So try and follow along. Okay, so you're going to be doing a lab. All right, you're already signed up, and you got accounts on this other website. that's for this other textbook, and it's called HMH, Holt, Mifflin, and something else. I can't remember. But the way you have to access it the correct way, or else you can't get in. You cannot access this website, which you need to for this lab, from the outside world. You have to access it through your HBUHD Gmail account. So you have to be logged on to your district Gmail account, right? Does everybody understand that? What that means? So yeah, you know, and you use your VPN, VPS, not virtual private network. That's something else. VPS, your standard password. VPC, right? VPC. You're going to be using your VPC to log on to your HBUHD thing, right? And then here's how you access the website. Does everybody know this little icon up here for Google Apps? Everybody seen that before? That's where you grab all the Google Apps. Please say yes. No? You've never seen Google Apps before? Okay, good. Yes, thank you. All right, so you click on that, right? And there's your Google Apps, there's your Drive, there's your Gmail, there's your, we don't use Classroom. There's your Docs, there's your Sheets. We don't, Meets is terrible. Calendar, you know, all that kind of stuff. Well, if you scroll down, can you see this? Down at the bottom, there's a whole bunch of apps down there that is not normally on a regular account, because we have G Suites and stuff like that. And we have other accounts. And so this is the way you have to, this is the only way to get into this website, is to go through this Google Apps thing. Does that make sense? So you'll notice that they've got this app here that's, I don't know why it's still there. This is the way you used to get into this website, but it's been disabled. So there's a big X, don't use that. So you're going to go over to this guy here, HMH. HBUHSD HMH. Everybody see that? Okay. All right. All right. And click on it. So I'm going to click on it. Okay. And it's going to go, actually, it should be, okay, can everybody see the my home page? Or are we still on the Google page? I have no idea. Let me go over to. Okay, now, yeah, so it should be, you should be seeing that. Okay, so you're seeing my. Let's try and move this over here. Let's flatten out a little bit because I've got it minimized a little bit. All right, so everybody see this? And this is very similar to or almost exactly what you should see. Okay. Now this is the regular high school textbook, not your textbook. So, there's some cool resources in here. Can everybody see my little hand? Okay, and it's on top of high school virtual physics labs. Can you see that? Or is my hand somewhere over on the other side of the page? So that's what it looked like when they're in the recording. It's on the left side. Yeah, so, oh God, I don't know what. So can you see the little pull down menu that says High School Virtual Labs? It's on the right side under Browse, and there's a little arrow there. And if I click on it, you see High School Physics Virtual Labs and then Physics 2017 Premium. Okay, the Physics 2017 Premium, I mean, you have access to it. You should all have access to it, and it's another textbook, but it's the regular physics textbook, and so it doesn't have any. Well, actually, it does have a little bit of calculus in it, which it shouldn't, but no actual calculus. But anyways, you're not going to be accessing that, so don't worry about that. You're going to be going to high school virtual physics labs, and then the icon, the red icon here says Launch High School Virtual Physics Labs. You see that? That should be there for you. Okay. Now I'm going to click on it. And it's opening up a new tab, and let's see if it worked. Okay, so I'm looking at my big blue bubble button, whatever it is, and I see Virtual Physics Labs. Okay, everybody see that? Virtual Physics Labs here up at the top. polyhedron learning media, hot Mifflin Harcourt, right? Mifflin. There's a joke there somewhere. Anyways, okay, so are we all seeing this stuff? Okay, so high school virtual labs. So there's a whole bunch of stuff on this website, and so what you need though to do this lab activity is go to, obviously, click on lab activities. Okay, and I click on that. Do you see that? Let's see if I. Okay, so I see lab. I'm seeing lab activities on my big blue button. So you should see lab activities, right? And it's a bunch of topics there. Motion, force, energy. That's what we're going to be doing this year. Motion, forces, and energy. We're not going to do fluids. We might do. What do we do under waves? We might do Hooke. We're going to do Hooke's law. So we might have motion of a pendulum and simple harmonic motion. Actually, we might actually do those because that's part of the course. But you're going to, for this first lab, you go to motion, forces, and energy, and everybody see the list of labs there. Okay. Okay. So we're going to go to acceleration of gravity. All right. Now this is going to, if I click on that, there's a link over. I don't know. It's over here. It says acceleration gravity, and so it's in that second thing. Let me go check. Just double check. Yeah, it's showing. Okay, it's showing there, right? Everybody see that? I have no idea where my cursor is on the screen for you guys. But it says acceleration of gravity. It's blue and it's underlined like most links are. Okay. All right. So now there's a bunch of resources down here if you want, but that's not what the lab is you're going to do. You're going to click on acceleration of gravity. Okay. Now it opens up something that you don't see right now because hold on a second. Okay. So I have to now, okay, I'm going to have to swing over here now and stop sharing webcam and then start sharing. Okay, let's go first. Is this it? Yeah, that's it. Okay. All right. All right. Now, do you see another guy? Do you see a guy falling, a skydiver falling? Okay. It opens up in a new window, so I have to go to this new window. Okay, now can you see my cursor flailing around that? Here's the guy. I'm going to try and pull his ripcord here. Okay, all right. And so there it goes. So in the blah 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 blah. Okay, so there's a whole bunch of links here: objectives, theory, pre-lab quiz, equipment, video, simulation, hands-on questions, support. Okay. You're going to go to the simulation. Okay, now there's a bunch. If you have trouble with any of the simulation stuff, you can check out some of these links there, and then they'll help you. Okay, there's a pre-lab quiz. Don't take it. I don't want that. That's not what I want. Okay, skip that. Okay, if you want to look at the video, look at the video. If you, I don't know what that but you're going to hit. What you're going to go to is the simulation. That's the lab you're going to do. And so I'm going to hit simulation right now. And it pulls up another different screen, unfortunately. So I'm going to have to stop sharing this screen and then start sharing the other screen. Which one is it? No, that's not it. This one. This is it. Okay. Here we go. All right. So everybody, do you see things says simulation instructions up the upper left-hand side? Under that is laboratories, and you see a little gizmo there in the middle. Does everybody see that? All right. Yeah, that's a lot of words. All right, so let me go back to. God, there's I got like 5 open screens here. They keep opening new screens instead of new tabs, which is annoying. All right, so simulation instructions. Okay, it tells you what's going to happen, what you're going to be doing, and so you play around. This simulation instructions, it just tells you what's going to be going on, and you can play. It tells you to play games with and how the controls work and everything. And then down here is the laboratory procedure, and that's the step-by-step instructions. Now over here is the actual lab. And there's the name, right? And I'm going to keep, so remember, the name, please do not put in acceleration of gravity. That's not the name. It's your name that you type in here, okay? All right, so you put in your name, okay? And then there's a whole bunch of boxes here for time selected, and this is all the stuff you have to figure out, okay? And so how does it work? Well, this is an actual simulation, right? There's a meter stick there. If you click the view, you can like zoom in or zoom out. Wait, what happened? I zoomed in. It's not zoom out. Zoom out's not working. You can go up, you can go down, you can go left, you can toggle right, and then you can reset it back to its original set and get rid of that. Okay, it's not really necessary for anything. But here's a little ball, and on the thing there's a little box there, and the box is a motion detector. Okay, which I actually have some of these. And if we were in here and doing a real lab, I'd actually make you do a real lab on this stuff. Okay. And so what do you do? Now I placed my cursor over the ball. Do you see it turn into a hand? Okay, so now that it's a hand, if I with my mouse, I'm using a mouse. Are you guys using a mouse or are you using the little trackpads? I don't know how it works on a trackpad. Do whatever the trackpad equivalent is of clicking and holding and clicking and dragging. You know how to do that? See, because watch what happens when I click and drag. I click and I can pick the ball up. Right? That makes sense? And then if I unclick, the ball drops, okay? And you notice it actually took some data. But I'm going to reset it, get rid of the data. So what you're supposed to do is follow the instructions carefully. You're supposed to drag this thing up here and then let it drop onto the box. And it takes data, and there goes my ball. Okay? Everybody see that? Yeah. Okay. So, if this were a real lab, I would have this thing. I would actually, it's an ultrasonic motion detector. It detects, it sends out sound. So till you leave the ball rolls off the table. Yeah, I know. In real life, I'd have to we have cars and they roll off tables. And I gotta, yell at everybody when they when they roll off the table. Anyways, I don't have to worry about it. It's virtual. I'm sure it doesn't. You hit reset and you get a new ball. Anyways, so here's the data, the simulated data that it took, okay? And it's height versus time, and it also does the velocity versus time. And you'll notice there's a little bit of problem with some of these times here, because if this is under the influence of a constant acceleration, what should the velocity versus time graph look like? What's the kinematic equation for velocity, in other words? Should look, right? Okay, so anyways, so you can see that there's a little issue there with the data. Maybe that was the bounce. I don't know. Maybe they simulate the bounce as well. Who knows? Anyways, all right. Now if you're what you can do is there's some points up here. Like let's see how many data sets. I actually dropped the ball twice, so I actually have 2 data sets. So you can look at the 2 different data sets. You only need 1 data set for the lab. And if you show data, it'll actually show you the numbers for the points on the graph, right? That makes sense? Okay. And then high data. And over here, there's curve fits you can do. So if I hit fit lines, it'll do a quadratic curve fit to the distance, height versus time, and then it does a linear curve fit to the velocity versus time. If I were doing this lab, I'd do it over again because something's wrong there. Anyways, but I don't know. Let's read. If I got time, I'm going to do this over again. Okay. Yeah, a little bit better. Okay, fit lines. Okay, so and you notice I got these little triangles, that you can use, and now that I've got that, I can do the area although it doesn't show it as a shaded region, which is kind of obnoxious. And I can change the area, right? And then here's another thing. Okay, let's say I want to find the tangent line. All right, what does the tangent line tell you that you need to know? Yep, there you go. Okay, so it's all there. And then you follow this guy, these laboratory procedures down, fill in all of this stuff. And there is one glitch that I will tell you about that they found out. Okay, so this is, okay, how much time? Okay, I've still got some time left. I'm going to try not to use up the entire period, but there's some things you need to know. And by the way, I haven't got this set up yet, so give me a day or two to set this up. I should have it done by the end of today. And then I'll give you a bunch of time to do this, just because there's going to be technical glitches. All right, if I click on percent, oh, I clicked on the wrong, well, there it is. Okay, so, you know, they want you to do the percentage difference between two values, which I suppose kind of makes a little bit of sense. Usually what do you do in a lab? You do the thing called percent error, right? It's like the difference between what you measured and what your theoretical expected or accepted value would be, right? And you find the percentage error. That's not what they're asking here. They're asking for a percentage difference, okay? Here's the problem. There's this formula for percentage difference there. And then where did they go? Up here, there's also a different percentage difference, but when you click on it, the formula is missing. So that's a glitch on their end, okay? But I think you guys are smart enough to figure out, let's just go Google percentage difference versus percentage error, and you'll figure out the difference between the two. It's not that complicated. All right, so when you get all these boxes filled in, right, what you're going to do here is, I'm going to maximize this thing out. Well, let me just try it here. You're going to go over here, and you're going to hit expand report. Okay, because you don't need the simulation. You've got all the numbers in your boxes. You've got your name filled in. And what you're going to submit as an assignment is basically an image of this report. And you're going to upload an image just like you upload your homework images in a Canvas assignment. Does that make sense? So there's going to be a Canvas assignment that says Acceleration of Gravity Lab. On that lab, there'll be a way of uploading an image file. Now the question is, how do you get an image of this guy? And there's various ways of doing it. Please don't take a camera picture of this. Somebody did that in regular physics, and it's really, when you take take your phone and take a picture of a computer screen, it's really, you get all these interference lines, and it's hard to read. So either do a screen grab, like, and there's various ways of doing it, or here's an option, at least in Windows, when you hit print report. This is kind of an older school thing. You can actually make if you have a printer at your home, you can actually make a paper print of this, and then you can take a picture of it, because then you won't get the interference lines. But one thing you can do, at least in Windows, when you hit print report, it gives you an option of where to print to. And one of the things is Microsoft Print to PDF, and it'll make a PDF of this file, which comes out perfect, and you can upload that PDF, and it's absolutely it's really easy for me to see. Okay, does that make sense? Print to PDF. Can you do that on Chrome? Windows Shift S, yeah. You can save the Google Drive on Chrome, okay, as a PDF. Yeah, perfect. Okay, that's what if you guys are using Chromebooks, that's what you got to do. Save the Google Drive on Chrome as a PDF. Okay, perfect solution. Okay, I'm on a Windows machine. That's what they gave me. So I'm on a Windows machine. So when I do print report, I say print to PDF, and then I would upload it to Canvas from my local computer. All right. All right, and that is it. That's what I want you to do. Now, when what's going to happen is when I get this thing online, the Canvas assignment, right? the Canvas assignment, which is going to look a lot like a homework assignment where you'll upload the file, will have in the instructions all of those step-by-step instructions on how to access this simulation. Go into your HB USG account, log in, go to the Google tab. So all of that stuff I went through, I've written it out step by step in case you get lost, okay? All right, and I'll give you plenty of time to get this done. So if you run into problems, technical glitches, we'll sort it all out. All right? So any questions about any of this stuff? Because that's where I want to leave it for today. Nope, I don't see anybody typing. All right. So if there's no other questions, we'll call it a day. And we'll see you guys back here on Wednesday, right? I lost my cursor. Today is Tuesday, Wednesday, Tuesday, Wednesday, Thursday. All right. All right. If no more questions, go ahead, log off. You got about 10, 12 minutes for your next period. And we'll see you on Thursday. Okay. I don't have a due date. When I do get the assignment put up on Canvas, it'll have a due date. Okay. But I haven't posted the assignment yet. So just wait till the assignment is posted, and then the due date will probably be next week sometime. Okay. All right. So we'll see you guys next week. Not next week, what am I saying? We'll see you guys on Thursday.